The opening of Star Trek tells us that space is the final frontier. But what it doesn't tell us is if space is real. Is it a thing? If you took all the matter and energy out of space, what's left? Seems like there are two possible answers: nothing or something. This is a long-standing question in the philosophy of physics. Those who say that when you take everything out of the universe, space is left, are called substantivalists. That is, they think that space itself is a substance. Those who say that nothing is left are called relationists, because they contend that space is not an independent thing, but just a set of relations among things. No things, no relations, so no space. This argument famously pitted two of the most intelligent humans to ever walk the earth against each other: Isaac Newton and Gottfried Leibniz. Both were physicists. Both were philosophers. Both were co-inventors of calculus. Newton had made his case in his masterwork, The Mathematical Principles of Natural Philosophy. In the opening section of the book, in which he sets out his theory of motion and gravitation, Newton argues that space is absolute. That is, a real thing that sits beneath the universe. In addition to space, he also argues that time is also absolute. That is, a real thing. If space is real, then there's an absolute location for everything in the universe. To move from one absolute location to another over a period of real time means that a thing has absolute motion. Location, velocity, and acceleration are, therefore, real aspects of the real world. The problem, of course, is that we cannot observe space, and that we only have access to relative measures of location, velocity, and acceleration. I could say that my car is 5 feet from the edge of a parking lot, and that I back out of my space at 5 miles an hour relative to the ground, but the ground is part of the Earth that's rotating on its axis and revolving around the sun. So the speed is a relative speed, and the location is relative to something on the moving Earth. These are not absolute claims, but relative ones. How can Newton justify a claim about the absolute nature of them? He says we can see it through its effects. To this end, he invites us to consider a thought experiment. Consider a bucket, half filled with water, hanging by a rope from a tree. Wind up the rope. First, hold the bucket still. At this point, the bucket is still and the water is still. There is no relative motion between them, and the surface of the water is completely flat. Now, let the bucket go. The bucket starts rotating, but the water in it is still. Now there is relative motion between the bucket and water, and the surface is still flat. Eventually, because of friction, the water will get dragged along, and the water will rotate along with the bucket. Because of the circular motion, the water will recede up the sides of the bucket, causing the surface to be curved. The bucket is rotating, and the water is rotating, so there's no relative motion between them. Finally, grab the bucket. Stop it. Now, the bucket is still, but the water inside is still rotating, so the surface is curved. Newton says, let's look at the results. In cases 1 and 3, there's no relative motion. In case 1, the surface is flat, and in case 3, it's curved. In cases 2 and 4, there is relative motion. In case 2, the surface is flat. In case 4, the surface is curved. The surface of the water does not at all respond to the relative motion between the water and the bucket. But the shape of the surface of the water does respond to whether the water itself is rotating. In cases 1 and 2, it's not rotating and the surface is flat. In cases 3 and 4, the water is rotating, so the surface is curved. So it must be the case that the water really is rotating, that is, in absolute motion. Absolute motion requires absolute time and absolute space. Thus, the shape of the water's surface shows us that space is real. Leibniz disagreed. He responded with a thought experiment of his own. Leibniz bases his own argument on a metaphysical axiom he calls the principle of the identity of indiscernibles. A thing is the sum of its properties. For a thing to be the thing it is for it to have all the properties it has. Two things are different only if they differ in at least one property. So if two things have all the same properties, then they're not really two different things. If there's no way at all to tell them apart, then they are the same thing. Leibniz says to take the universe and switch east to west and west to east. The contemporary philosophers set up the thought experiment this way. They use translation instead of reflection, but it's the same argument. Take the entire contents of the universe and shift it all 3 steps to the right. Is it any different? Leibniz says no. The universe, its history and future, every single event, every single geometric and physical relation, everything is the same. The universe here and the shifted universe are indiscernible. Therefore, they are identical. And if the original and the shifted universe are the same universe, then there can't be a real space underneath, or else they wouldn't be identical. Things would be at different real locations. It would be as if you and all your neighbors shifted one house down the block. You'd have a different house. But that's not the case. So, space is not a real independent entity, just the set of relations among the real things that make up the universe. Needless to say, these competing arguments did not convince either of the competitors. At the end of the 19th century, the Austrian physicist Ernst Mach sought to create a worldview based entirely on science. He called it positivism, and held as a fundamental postulate that the only things we should say exist are things we observe. Seeing is believing in a deep sense. We don't see space, so there is no space, only the things in space that we do see. He sided with Leibniz, but he realized that Newton's bucket argument required a response. It's a great argument. He had to concede. We do only see the surface of the water change when the bucket's rotating. Newton is absolutely right about that. How then could he be wrong about the fact entailing the necessary existence of an invisible space? The water recedes up the sides of the bucket when it's rotating. But we need to think of a way that makes that rotation relative. Relative to what, if it isn't an absolute space? What is in that absolute space? Stuff, and lots of it. Some of it very large. Stars, which might be very far away, but which are incredibly large and which number in the billions and billions, all of which, being massive, have gravitational effects. The bucket is rotating with respect to these stars and the billions and billions of gravitational components they project. The bucket rotates relative to the fixed stars, and this can be used to explain the change in the shape of the surface of the water only in the last 2 cases, but without having to posit the existence of a real space. Done. One person who read and was deeply influenced by both Mach and Leibniz was Albert Einstein. He thought they were right about space, and their direct influence on the development of the theory of relativity is obvious once you know what you're looking for. The theory of relativity is first proposed by Einstein in his 1905 paper on the electrodynamics of moving bodies. Now, in this paper, one of his interests is undermining the belief in the existence of a luminiferous ether, that is, an electromagnetic version of Newton's absolute space. Einstein is going to start the paper with a thought experiment that intentionally sounds exactly like the thought processes of Mach and Leibniz. In the experiment, Einstein invites us to consider a circuit that contains a coil of wire. We take a magnet and move it back and forth through the coil. What happens? An electric current is generated. Now, keep the magnet still and move the coil back and forth at the same rate. What happens? Exactly the same thing. It doesn't matter which one is moving as long as the rate is the same. But the classical explanations are different. When we move the magnet, the current is the result of a changing magnetic field. When we move the coil, it's the result of motion in a static magnetic field. Different descriptions, but the measurable results are indiscernible. The two, Einstein argues, are just different descriptions of the same physical situation. And if the physical situation is the same, then there's no underlying truth about motion relative to the underlying electromagnetic space. There is no absolute space, only relative space. The original theory of relativity, what we call the special theory of relativity, justifies Leibniz's and Mach's relationism. The result of this shift forces us to change our view of mechanics, the physics of motion. Doing this has all the strange results we know about from the theory of relativity. We get the Lorentz contraction, the effect discovered by Einstein's hero, H.A. Lorentz, according to which objects contract in the direction of motion when viewed by an observer outside the reference frame of the moving object. When two observers are in motion relative to each other, time passes at different rates. If observers are moving relative to one another, they'll disagree about the mass of a given object. This alteration gives rise to the most famous result of the theory of special relativity, the equation E equals mc squared, according to which mass becomes just like heat or motion, just another form of energy. For us, though, what's important in this conversation is that the foundation for all of these peculiar results is that it stems from a reasoning process that accepts the Leibnizian view of relationism. In special relativity, space is not a thing. But Einstein wasn't satisfied with special relativity for two reasons. First, the relative motion that it accounts for is limited. The equations only hold for observers who are moving in a straight line at a constant speed. Acceleration should be accounted for if this is to be a general theory. Second, the theory includes mentions of every single force known in the universe except one: gravity. Why should gravitation be left out of the party? Einstein needed to generalize the theory of relativity in a fashion that accounted for acceleration and gravitation. How to do it? It wasn't going to be easy. He quickly came to realize how hard it was going to be, saying that this problem was so hard that it made discovering the special theory of relativity seem like child's play. The key came to him while looking out the window one day while he was at work in the patent office. He saw someone on a ladder washing the window. It was then that Einstein had what he later called his happiest thought. The thought was, what would happen if he fell off the ladder? To us, this is a horrible thought because our minds immediately go to the landing where, at best, the poor fellow breaks a leg. But that's why Einstein was Einstein. He thought not about the landing, but about the falling. While falling, he realized the window washer would not feel his weight. Free fall in a gravitational field and floating stationary where there is no gravity are indiscernible. Using Leibniz's principle, they're identical. Acceleration and gravitation are not two different problems he had to solve. They were the same problem, just seen from two different directions. He had to account for gravity in terms of accelerated motion. They were the same thing. Again, note the use of Leibnizian relationist reasoning here. This insight led ultimately in 1916 to the general theory of relativity. The general theory of relativity gives us a new theory of gravitation that replaced Newton's old view, according to which gravity is a force between any two massive objects that are separated in space. According to Newton, mass is absolute and distance is absolute, and so the force of gravitation across space is absolutely determinable. The force travels across space, but is not influenced by space. Space is real, but doesn't interact in any way with the stuff in it. It was abandoning this last part that was the key for Einstein. Space is influenced by the stuff in it and also influences that stuff in return. The effects of this relationship are geometrical. Matter and energy warp space, cause it to curve. This curvature then determines how objects move in space. Newton saw space as an infinitely long and infinitely wide frictionless pool table. Because it's infinitely long and wide, the stuff in space would never reach a bumper and change direction. And since it's frictionless, the space would never cause the stuff in it to change speed. Space is just where the stuff is, but has no effect on it. Einstein saw space as more like a trampoline that sags and warps with the weight of the stuff on it, changing its shape in a way that can cause things to change how they move. Space, in the general theory, is dynamic and interactive. This difference between Newton and Einstein, flat versus curved space, had the effect of giving rise to conflicting predictions in observable circumstances. The observations were carried out, and Einstein's predictions proved to be correct. So it seems we must therefore conclude on the basis of observable evidence that space is, in fact, curved. That's the physics. But what was interesting were the philosophical ramifications of it, one part of which became immediately apparent to Einstein. If we say that space is in fact curved, then we're saying that space has a property, the geometric property of being curved. But a thing is defined by its properties. If we're attributing to space the property of being curved, then space has a property. And to have a property means that it's a thing. Einstein's general theory of relativity seems to entail, contrary to Leibniz and Mach, the people who deeply influenced Einstein's thinking, that space is real. Space exists. Where the special theory of relativity seems to support Leibniz's relationism, the general theory of relativity seems to support Newton's substantivalism. We see evidence of this change in Einstein's own view in a talk he gave entitled Ether and the Theory of Relativity. The talk was given on May 5th, 1920 at Leiden University in Holland. In attendance at this talk was none other than H.A. Lorentz. Remember, Einstein's hero, after whom the length contraction effect in special relativity is named. Einstein was giving a talk about the theory of relativity in front of his hero, a hero who rejected the theory of relativity, in part because he believed so deeply in Newton's absolute space. In this talk, Einstein explains how his new version of the theory of relativity differs from the old one, and that difference is that the curvature of space seems to bring back a version of Newton's absolute space. So it seems like a change from the special to general theory of relativity is a change in which Einstein himself changes sides from the relationist to the substantivalist. A group of philosophers we mentioned in the first lecture, the logical positivists, were deeply influenced by Einstein as well as Leibniz and Mach. They were not so quick in the face of this new version of relativity theory to adopt the substantivalist viewpoint. They still thought that space is not a real thing unto itself. Their argument reached back to another of Einstein's heroes and influences, the French mathematician, physicist, and philosopher Henri Poincaré. Poincaré came up with a thought experiment. He said, think of a flat world that's entirely on a disk. Suppose that everything in this world is made up of the same substance, including the intelligent beings who live there and who have minds like ours. Also suppose that the center of the disk is always heated to a temperature of T, let's say 50 degrees, while the edge of the disk is at absolute zero. Now, as things get colder, they contract. These intelligent beings would be interested in their world and would try to measure it. Now, how do you measure something? You take a measuring stick and you put it against something and count the number of times you have to move the stick. If your measuring stick is 1 foot long and you want to measure the length of a wall, you start at one end of the wall and see how many times you can put the stick down in a series until you reach the end of the wall. The number of times is how many feet long the wall is. Trivial, right? So, the beings start at the center and carry this process out. How many times will they put the stick down before they reach the edge? Since with each step towards the edge, the stick gets colder, with each step it continually contracts, getting smaller and smaller each time. As a result, they could put the stick down an infinite number of times and never reach the edge. They would therefore say that their world is infinitely wide. We would politely explain to them, no, your world is finite, but the stick shrinks. They would respond indignantly that the stick is exactly the same length they are, and look, it always remains so. But we would object, no, you shrink too. No, I'm always the same length that I am. Poincaré is arguing that physics presupposes a geometry, and that geometry presupposes a physics. It's a circle we can't get out of scientifically. What do we have to do? Define our way out. Pick one. If you pick a geometry, then you can empirically develop a physics. Pick a physics, and the geometry becomes an empirical science. But, and this is the key, the choice is free. It's a convention. That is a mere definition, something we impose on the world, not something we learn from the world. The logical empiricist Hans Reichenbach was one of Einstein's friends and a former student. Reichenbach was one of the small handful of students who took Einstein's very first seminar in the theory of general relativity at the University of Berlin, and Einstein personally handwrote comments on a pre-publication draft of Reichenbach's first book. I actually got to hold that book in my hand once, looking at Einstein's comments written neatly in pencil in the margin. Reichenbach adopted Poincaré's argument to Einstein's new theory. Einstein says that gravitation is not a field in space, like Newton thought, but a curvature of space. But, Reichenbach argues, we could think of the curvature itself as a field. Which field do we want? Do we want a flat space with a gravitational field that shrinks objects, or a curved space with a gravitational field that doesn't? Does it matter? To determine if it matters, Reichenbach reaches for Leibniz's principle of the identity of indiscernibles again. There's no difference between the two, so the two are not different. The decision is not something that tells us how the world is, just how we go about linguistically describing it. Should we use meters or feet? Just pick one. Whichever you pick is fine, and the choice doesn't change how long the wall is. We just need to know which stick to lay down in measuring the wall. It's just a linguistic choice. The result? Curved or flat space? Not a real difference. If it's not a real difference, then it's not a real property. If it's not a real property, then space is not a real thing, and we've rescued Leibniz and Mach's relationism. Some contemporary thinkers have sought to undermine this conventionalist approach, arguing that even though the curved space theory and the flat space theory give all the same predictions, there's still philosophical reason to prefer the curved space version. That means that we should attribute a geometric property to space and hence hold that space exists as a thing. Clark Glymour, founding father of the Department of Philosophy at Carnegie Mellon University, and Michael Friedman, professor at the University of Illinois, Chicago, contend that we should buy into the idea that space is real, even though there are flat and curved space theories that make all the same predictions. The grounds they cite are various versions of Occam's razor. Occam's razor is the principle that when faced with two alternative theories, we ought to prefer the simplest one. By simple, it's meant the one that posits the fewest entities. Since saying something exists is an assumption, and assumptions can be wrong, we're least likely to be wrong when we make the fewest assumptions. So, prefer theories that employ the fewest entities as real. Different philosophers have made this case in different ways. Let's look at just two of them. Michael Friedman wrote what is surely going to be seen as one of the true classic books in philosophy of physics, Foundation of Space-Time Theories, Relativistic Physics, and Philosophy of Science. In this book, Friedman axiomatizes the theory of relativity. That is, he comes up with the most elegant set of basic sentences that allow us to describe the content of both the special and general theories of relativity. In doing this, it allows us to directly compare the curved and flat versions of the general theory of relativity. Now, if you're watching this course on video, you'll see the equations on the screen. If you're listening in audio, you'll find them in your guidebook. While the details are very technical and we won't get into them here, what's important for us mathematically is simply the ability to count. Notice that the curved version has one fewer axiom. The game here is like golf. The smallest score wins, and curved theory has 3 to flat theory's 4. Curved theory wins by 1. The reason for this is that Einstein creates the curved space by combining 2 elements: the curvature tensor that describes the geometry of space and the gravitational field. By squishing these 2 into 1, there's now 1 fewer element, and thus we need 1 fewer axiom. The flat version separates the 2, meaning we need an axiom that says that the geometry is flat and another that accounts for the gravitational field in the flat space. We need 2 axioms to do the work of Einstein's 1. We're making the assumption of 1 more existing entity. By a version of Occam's razor, then, we should prefer the curved version. Space has a property, and so space is real. Others have offered arguments on the other side, maintaining that even though there seems to be actual claims about the geometry of space in general relativity, we should nonetheless maintain a relationism like Leibniz. This is the view of the 3 Johns: John Ehrman and John Norton, 2 members of the faculty at the University of Pittsburgh, and John Stachel, who had been at Pittsburgh but ended his illustrious career at Boston University. Their attack on substantivalism derives from a historical quandary Einstein himself had to overcome in developing the general theory of relativity, the so-called whole argument. The argument begins by positing the existence of a universe that's perfectly described by Einstein's theory. Every event that occurs is perfectly accounted for using general relativity. In this universe, the 3 Johns tell us to find a whole, that is, a small volume of space far away from everything else where nothing is happening. The whole is a region of space completely free of any occurrences. There are no particles to bounce off of each other, nothing, just a region of empty space. Inside this whole, they show, it's possible to take the geometry and twist it, thereby changing the gravitational field values inside, but keeping them the same on the surface of the whole and the rest of the universe. The equations of the theory, they argue, would account for the twisted whole in exactly the same way as it does the non-twisted whole. Since the whole is empty, there's nothing different to explain. But the substantivalists argue that the explanation necessarily attributes a specific fixed geometry to space, and this property forces us to consider space to be a real thing. The property that is supposed to give us a reason to think that space is real is its shape, its geometry. But now, with the twisted and untwisted wholes, we have 2 different geometries equally well described by the same output of a single theory. The theory does not uniquely and completely determine the geometry of absolutely all of space. So, there seems to be no reason to attribute the geometric property to the space. But if space is not forced to have a shape, then it's not forced to have a property. And we're not forced to think it's real. Substantivalism makes an extra, unnecessary metaphysical claim. Occam's razor, therefore, does not force us to think that space is real. To the contrary, it forces us to reject the reality of space. We're back to relationism, back to Leibniz. While Ehrman, Norton, and Stachel are 3 of the smartest, best known, and most widely respected figures in philosophy of physics, A different argument in favor of this view was advanced by someone generally thought to be the funniest and best-looking thinker in the field. Yeah, that's me. Don't ask, it's an old picture. In my contribution to this debate, I've contended that the move to use Occam's razor on the two versions of the general theory of relativity doesn't quite work the way Friedman and Glymour think. The trick they're employing is to say that flat space is space with zero curvature. They use complicated numerical representations of geometry, what we call tensors. Flatness in geometry is achieved by setting the central term in the tensor representation equal to 0. What does it mean to set something equal to 0? Well, on their read, it means to say that something does not exist. Suppose you asked me what kind of cars I own, and I respond with, I own a number of Rolls Royces. And you then ask me, what number of Rolls Royces do you own, Steve? And I say, the number is 0. I am clearly being silly at best, nonsensical at worst. It isn't that I own a number of Rolls Royces and the number is 0. The simple truth is I don't own Rolls Royces. There's no reason for Rolls Royce to be any part of this conversation. In the same way, Friedman and Glymour argue that the flat space version of general relativity says that there's a curvature and the curvature is 0. There's no reason for this extra thing to be part of the conversation. I argue that this is wrong. It's a flaw introduced by their means of representing the theory. To say that the curvature is 0 is not like saying I own a number of Rolls Royces and that number is 0. Rather, their contention is that flat space having 0 curvature means there's no geometric entity necessary for the basic set of assumptions underlying the general theory of relativity. And that's a lot like someone saying it's 0 degrees Fahrenheit outside, therefore there's no temperature. 0 degrees doesn't mean 0 temperature, it's a relative scale. Same with curvature. Flat space still has a geometry, just one represented in your system with the number 0. 0 doesn't represent an amount, but a degree. If this is true, then there's still the same number of assumptions, and the appeal to a version of Occam's razor won't help us in the way they think it will. But this means we're back to Reichenbach and Poincaré's position of just having to choose conventionally between two different linguistic presentations. Space no longer has a property and therefore isn't real. Am I right? Are they? Does space have a geometry? Come back for the next lecture and we'll see what kind of shape we're in then. Get it? Shape? Geometry? All right. At least I'm still the best looking.